Welcome to Summarize Science. Astronomers are hunting for gravitational waves, which are faint ripples in the fabric of space-time itself. One of their best tools is a pulsar, a superdense dead star that spins hundreds of times a second, flashing beams of radio waves like a cosmic lighthouse. By precisely timing the arrival of these pulses, we can detect the tiny stretching and squeezing of space caused by a passing gravitational wave. However, this is incredibly difficult because any error in our calculations can mimic or, even worse, hide a real signal. The biggest problem is knowing exactly where the pulsar is. If our map of a pulsar's position is even slightly off, it creates errors in our timing that can look like noise. When scientists try to clean up this noise, they risk accidentally removing a real gravitational wave signal along with it. This paper presents a clever solution to this problem. They use a completely separate technique called Very Long Baseline Interferometry, or VLBI, to get hyperaccurate positions for these pulsars. VLBI links radio telescopes across the globe to create a virtual telescope the size of the Earth, allowing for incredibly sharp images and precise measurements. But there was a catch. The pulsar timing method and the VLBI method use different coordinate systems, like trying to use two maps with slightly different north poles. So, the researchers first had to calculate a precise frame tie, a way to translate the coordinates from one map to the other. Once they aligned their maps, they could use the ultra-precise VLBI data as a guide for their pulsar timing models. This created new, more robust astrometric solutions for 18 pulsars in the NANOGrav 15-year dataset. These plots show how well their new combined data, in green, agrees with the old timing data, in blue, confirming their method worked. And here's the most exciting part. When they compared the results from their new model to the old one, they found clear, periodic signals that had been missing before. This top graph shows the difference between the old and new models over time, revealing a distinct wobble. The graphs below show that this hidden signal has strong peaks at frequencies corresponding to 1 year and 6 months. These are the exact frequencies where errors in a pulsar's position and parallax would show up. This means the old models were absorbing real power at these specific frequencies to make the data fit, potentially erasing signals from things like orbiting supermassive black holes. For example, a famous galaxy called 3C66b is thought to have a binary black hole with a period of about 1 year, a signal we haven't found yet. This work suggests we might have been accidentally filtering it out. So let's recap. By combining two powerful techniques, scientists have created a more accurate cosmic GPS for pulsars. This new method prevents the accidental deletion of signals that could be from gravitational waves. In the future, this will make our search for gravitational waves more sensitive, especially for specific targets, and bring us one step closer to understanding the most massive objects in our universe.